Hello everyone, and welcome to episode 4 in my series on arbitrary precision arithmetic. Today we're going to be covering the algorithm for long multiplication. So, what is long multiplication? This is an algorithm just like long addition and long subtraction that we've covered, which is very similar to the algorithm for multiplication that's taught in many schools. This is algorithmically equivalent to the method that's called long multiplication that's learnt in grade school, which is shown here, and lattice or sieve multiplication, which is a different looking method. However, in terms of the algorithm, it works out the same. So, right at the start of this, we're going to go through a decimal example. So we're doing 8,174 multiplied by 537, and we're iterating through the digits of 8,174, which means first we are multiplying the least significant digit, which is 4, by the least significant digit of the second number, which we're also iterating through. So first of all, we have a carry variable that we have to keep track of, since we have to carry over the result of the multiplications into the next number. So initially we just set the carry to 0, as I've shown on the left hand side of the screen. And now we do the multiplication of single digits, 4 times 7, which is equal to 28. And since we have no carry, we just add nothing to the 28, and that's our final result. And we get a new carry by an integer division, dividing the result by the base, which is 10. So 28 divided by 10 gives 2 and a remainder, which is 8. So 8 is set to the first digit, and the 2 is set as a carry. Next, we move on to the next digit in the second number being multiplied, and therefore we're doing 4 times 3. Now, since we already have a carry 2, we have to add this to the result of 4 times 3, which is 12, and when we add 12 plus 2, we get 14, which means that the carry is now 1, since 14 divided by 10 is 1, leaving a remainder 4, which we set as the next digit to be added. And then we continue the same process. We carry over the 1 from the last operation. We multiply the next pair of digits 4 and 5 to get 20. We add the carry, 21, and we divide it by the base to get the next carry and the remainder, which is the next digit. So we have 2 as the carry and 1 as the remainder. Now we've finished that first iteration through the second number, so the next thing we do is move on to the next most significant digit in the first number, and we go all the way back to the end of the second number. Since we are at the end of the iteration, the carry is just added to the total and reset. What we do is we get a list of different multiplications of the second number by each of the digits of the first number and add them together at the end. So, without further ado, we have the next pair of digits, 7 times 7. Since the carry is reset, it's just 7 times 7, which is 49, and we divide that by the base 10 to get our next carry, 4, and our remainder, 9. The carry is 4. We move on to the next set of digits in the iteration, 7 times 3, which is 21. We add the carry 4, which is 25. Then we divide by 10, which is 2. So this is the general process, and we're going through a lot of multiplications, a lot of steps. So I'll just quickly display this on the screen. As you can see, we keep going through the digits. And the same thing happens here when we reach the end of an iteration. And here again. And here again. The last multiplication in the procedure. So as you can see, we've been shifting the multiplications of the second number by each of the digits, and that is because when we multiply the second number by each of the digits in the first number, as we go further up through the digits, represent higher values than the previous digits. In fact, they're one base above the previous digit, so each time we shift the result over, and then finally, the products of each iteration are summed. In the programmed algorithm, this is normally done within the iterations, so that we don't need to keep storing each of the products into different places every single time we do an iteration. So now we'll have a look at what is the time complexity of this algorithm. The time complexity of long multiplication is on the order of n squared, where n is the number of digits, where n is the number of digits in a number being multiplied. And this is because of the nested iterations. If you remember, we iterate through the first number. But then, within each iteration of the first number, we also iterate through each of the digits of the second number. So each time we multiply the time complexity by a factor of n, the amount of digits in each number, which produces n squared, the fastest growing term in the algorithm. So don't worry if you didn't understand that completely, because now we're going to go through the programmed version of this algorithm, more of a general look at how the algorithm works. So here we are in the bignum class, and we have a method, long multiply. We're multiplying by the multiply, and first of all we just set a and b to be the digits of the first number and the second number for brevity. Then we initialize the set of product digits with zeros. So this means that we're just getting a list of zeros, which is the sum of the length of the two numbers, which is the maximum length that we can have for a product. So then we iterate through the first number's digits, as we've said. It's just an iteration. And the first thing we do is we reset the carry to 0. Very important, as it resets every time we restart multiplying one of the digits of the first number by the entire second number. And then we iterate through the second number's digits. And the first thing we do is we add the product of the digits and add the carry to the final product. So this is what we're doing. We're getting the carry and we're adding it to the first number's digit multiplied by the second number's digit. And look at where we are placing the digit in the list of digits. It's the position in the iteration of the first number added to the position in the iteration that we are in the second number. And if you go back in the video and look at the example, you will see that if you start with the least significant digit as 0, the next most as 1, the next most as 2, etc., and you compare the position we are in the iteration with the position we are in the product, you will see that this works out every single time. And that's because for each iteration that we do, each of these iterations, we are multiplying by the base. We are going up by one digit, which is essentially the same as multiplying by one base. If you go up by one digit in base 10, you're multiplying by 10. If you go up by one digit in base 2, you're multiplying by 2. In this system, we're multiplying by 2 to the power of 30. And then we calculate the carry, as we have done. We set it to this result, the sum of the carry and the product of the digits, divided by the base. And as you can see, we've used integer division, We only want an integer. We only want the first digit in the product. And that's how we get the carry. And then we modulo the digit in the product, meaning we get the remainder, so that only the last digit remains. We are doing the modulo of this by the base. And that's the end of that iteration. And then once all of these iterations, all of the iterations through the second number's digits are done, once we have multiplied one digit in the first number by all of the digits in the second number, we get the next most significant digit from the final carry. So we basically set the last carry to the carry that's left. And then, of course, we reiterate, we reset the carry, we do this again throughout the entire number. Once we're done, we just return the number that we have. And now we're going to go through a couple of tests that I've written. I've written a nice file, as we have in previous episodes. So let's hop right into that. Okay, so here we are. And let's just type, run this multiplication test. And as you can see, we first have a small multiplication, only 25 times 25, which must be single digits in this system. And as we can see, this is equal to 625. So with single digits, it works fine. You just do one iteration. We have a bit of a larger pair of numbers. We have 1, 2, 3, 4, 1, 2, 3, 4. So what? That's 12,341,234 and 2,000 million. And when we multiply them together, 2468, 2468, and then 9 zeros. So now we have a bit of a smaller number and a bit of a larger number. When we multiply them together, we get this number. I can't work that out off the top of my head, but it should be the correct answer. You can download the test and the source code for the algorithm itself on my GitHub. Just like every single episode, you can download the entire backlog of episodes on there. So thank you all for watching. Leave a comment if you have any questions or if you have any suggestions or criticism for me. Leave a like if you like the video and subscribe if you want to see more. Next episode, we'll be covering another multiplication algorithm, the Karatsuba algorithm. Slightly more complicated, but we'll have a look at why you might want to use this algorithm or why not. So that's it for this video, and have a great day everyone.